I would be giving this talk in English only, but we'll go slowly, and we can always invite questions, of course, at the end or during the talk. I'd have this thing right in the middle of my screen. I'm just going to get rid of it. Okay. All right. So today, I could spend many hours and days talking about stable isotopes and to really bring you through this application. But this will be a very brief talk to just, if you like, whet your appetite, just get you interested in the kinds of things we have been doing. So there's been a lot of talk recently about, well, isotopes are no longer needed because we can put all these lovely devices on migratory birds and so on, and we can track them electronically using geolocators or satellite tags or what have you. And that's a field that has exploded recently. And so I get a lot of people saying to me, well, we don't use isotopes, they're not very accurate, and what's the point? Today, I'm going to convince you that there are still some possibilities for using isotopes, especially in Africa and other continents. So I will tell you about that, and then I'll introduce briefly the basic principles of stable isotopes. And again, if you don't quite get that, that's okay. We can always come back to that, and that's a learning process that we can always get to in the future. And then I'll spend a fair bit of time talking about applications to animal movement involving Africa, the work that I have been doing in particular, and we can end by some reminders of where we think the field is going. Well, most of my research has been on birds, and so I'll give you some insect examples, but I mostly work on birds. And you will know already that, again, these days there are many, many ways of marking birds using satellite transmitters like this on large birds that can carry the weight, all the way down to using these little light-sensitive geolocators and so on, as well as banding or ringing that you can see here. So there's been this great interest in tracking individuals. Of course, we've done this work with barn swallows that I show you here. The only problem with the geolocators, of course, is that you need to retrieve the bird a year later. So you have to get it again. And you can only, really equip a small number of individuals through time. So really, rings have been the mainstay of tracking bird movement, as you know, and Europe and the Europe-African migration system has really relied extensively on numbered bands or numbered rings. And it's been extremely impressive. It's just amazing how many birds have been ringed and all of the wonderful information that's come from that application. Now, not just birds can be marked with these so-called extrinsic markers or external markers. Chip Taylor here of an organization in North America has put tags like this on monarch butterflies. And monarch butterflies are an iconic migratory butterfly in North America that goes about 4,000 kilometers from North America down to, well, Canada and the US down to these wintering sites over and wintering in Mexico. So these little numbered tags have been used for many years now. And here is Chip going through a big pile of dead monarch butterflies that accumulate. These have died naturally under the roosts of the trees in Mexico over winter. And he's going through them looking for one of these tags. So it's a bit of a needle in a haystack, is what we would say. All right, so there were ways of marking individuals. And of course, with these geolocators and new technology, this is work we've done out of Colombia and South America. You can get beautiful tracks like this if you can recapture the bird when it returns again the next year. And so over the years, we put together 10 or 12 of these tracks, and we've got these lovely patterns. And I'm here to tell you that you can't beat this, okay? You cannot beat this. This is the state of the art tracking of an individual. And isotopes cannot come close to this kind of resolution. However, there are many opportunities and many situations where you cannot do this kind of work. Here is another example closer to home now in Europe, where these folks in Switzerland actually have summarized all of the geolocated data they could get their hands on from Europe. And these are all species. These are not just one species. And they have demonstrated through geolocators alone that there's this migratory divide in Europe, the Afrotropical, Palearctic Afrotropical migration system, where you get this lovely split. And this is based again on these exact points of where you know where these birds went. So this again is beautiful stuff. And I'm here to say, though, that there are a number of occasions where you do not have markers on birds. And a classic example is, of course, the avian influenza virus, where it's of great interest now. The dark values here are the ones where human fatalities have taken place as a result of avian influenza virus. So there's a lot of interest now in zoonotic viruses, etc., that have spread or at least involve wild birds. So if you found a dead bird in Europe and you're asking, well, where did you come from? The chances of it having a ring on its leg would be pretty remote. And so we are finding that using stable isotopes to put together migratory patterns of birds with zoonotic diseases, for example, would be a great application. The other one, of course, that some of you will be familiar with, is, of course, is the illegal trade in wildlife parts. And there's a great interest in using forensic tools to figure out where an animal came from. Again, none of these animals will be marked. They will all be confiscated, and none of them will have bands or little markers on them to tell you where they came from. And so there's a lot of interest in trying to come up with techniques where you could take a little hair sample or a feather sample and say, we think this animal is from here versus here. And in a court of law, quite often, that's all you need to know. Okay? Well, the advantages of intrinsic markers are those are markers within the animal, okay? These are markers that they take with them all the time, don't require us. They're not biased to origin. That means it doesn't matter where they came from. We can infer that information from this intrinsic marker. Only one capture is required. You don't need to recapture an individual. Only one capture is required. You can gain information on thousands of individuals relatively inexpensively compared to some of the technologies that are coming out. And importantly, I think it doesn't influence behavior, because you're only inferring information of origin of these animals after you've captured them. So it's the information they've carried with them, and they haven't had to lug around this piece of equipment for 11 or 12 months. Okay. So that's the advantages of intrinsic markers. There are disadvantages as well, and we'll get into those. But what have we done here? We've used naturally occurring elements, isotopes of naturally occurring elements. And these are the so-called light elements: carbon, nitrogen, sulfur, oxygen, hydrogen. And they occur in more than one stable form. They occur most commonly in these yellow forms, but they occur very rarely in a heavier form. Now, these don't go anywhere. They're not radioactive. They're stable. They are around forever. They've been around forever. And we're interested to know what the ratio is of the heavy to light isotope. Now, these are very, very tiny ratios because the heavy isotope is very, very rare. But by knowing how the heavier to lighter isotope behave in natural systems, we can infer all kinds of information. So we look at that ratio and we depict it with this weird delta notation like so. You don't need to worry about this. All you need to know is that what we're really doing is figuring out how these two different isotopes behave in nature, and in particular, how the heavier isotope behaves relative to the lighter one. Okay, now there's all kinds of machinery you can use to do this, mass spectrometers and so on, and I won't go into that, but rest assured that this is a field that's been around for like 50 years now, 50, 60 years, and there's lots of really cool gadgets you can use to do this. Well, some of you may know this is my "You are what you eat" slide, okay? And what we're going to look at here is these isotope ratios occur naturally in food webs in nature. And how do they get into your body? How do they get into the bodies of insects, birds, what have you? Well, it's basically through primary production, that is through plants. So plants fix carbon, nitrogen, well, actually not, yes, they do fix carbon, but from atmospheric sources. But the point is that these isotope ratios will enter food webs and then travel up the food web, going from primary production to the primary herbivore to a primary carnivore and so on. This is just a trophic relationship up a food web. And if we were to measure the isotope ratios of a consumer here in these tissues, and if we knew how these isotope ratios changed as you go up a food web with these large delta values I'm showing you here, we could work backwards. We could say, we think we know what these sources are that you've depended on, or what mix of these sources are that you depended on to make your tissue. And luckily for us, many of these isotopes change as you go up food webs because there's all kinds of biochemical processes that result from respiration, excretion, where one isotope is preferentially lost over the other. So we can start putting together a story about what the primary productivity looked like that went into this consumer all the way up a food web. Okay, well, as you know, consumers are not just made up of one tissue type, they're made up of tissues that turn over at very different rates. Some very fast, like liver, plasma, others very slowly, like bone collagen, etc. And we can make use of that if we imagine just changing the diet from one isotope value to another, which I show in the top graph here. We will know that some tissues really follow that very quickly because they're turning over so quickly, like liver. But these other tissues turn over much more slowly. And our choice then of the tissue that we want to look at will give us a different time period of integration of what we're looking at. So that's all I'm going to say about stable isotopes. I'm just going to tell you that, your choice of tissue and knowing what those changes are through a food web can tell us an awful lot about animals and where they come from and what they've been feeding on. Okay. All right. Well, luckily, I and others have been working on this for some years, and we've raised animals in captivity to work out these relationships. We've switched their diet. We played all kinds of games, and we've worked out those relationships for a vast number of birds and other organisms that you can see here. These have all been raised in captivity, and we've done these kinds of isotope studies on. Now, for a bird or an insect that is migrating, we would be particularly interested in a tissue that doesn't turn over. In other words, once it's formed, it's locked in so that you could lock it into a source. Now, that is true of hair, claws, feathers. These are tissues that once they're formed, they don't change anymore. So they've locked in that food web signature of the place where they were formed. And this gives us a great technique for then taking that tissue and working back and saying, where were you formed? What kind of conditions under which were you formed? What kind of diets went into you when you formed this tissue, etc. So often in migratory studies, we'll be using bird feathers because they are formed, grown, and then become metabolically inert after that. For insects, we will use their wings, which represents really the larval diet, the caterpillar stage, goes into the adult stage, and that wing doesn't change very much at all after that. In fact, you can go back to museum samples and recreate a number of these factors. So we often are looking at these non-metabolically active tissues to recreate these kinds of scenes. So equipped with a knowledge of isotopic discrimination at large delta value, these turnover rates that I've told you about in time, and a few other things about the biochemistry of diets and so on, we have this lovely application to go backwards and look at food web applications. One of those is not just what you're eating, but where you were eating, okay? And I'll get into that in a moment. And this is some data from, this is years old now, it's probably about 30 years old, from Argentina. These are 3 species of gulls. They're all lariat gulls. They're all very closely related. And they're all occurring in the same place: Olrog's gull, kelp gull, dolphin gull. And what we've done is we've run the carbon isotope values of their blood and the nitrogen isotopes of their blood. And all you have to do is look at this and say, each of these species is doing something very differently. And these are some now have come up to be called isotopic niches. And we can simply say, you must be feeding on X, you must be feeding on Y, and Z, and so on. And so we can start teasing apart even closely related species and ask, how are you using the environment? And a whole lot of isotope applications do that. Part of that would be where as well as what. Now, this brings me into the whole idea of isoscapes, okay? Now, this is a word that's been coined, but basically it's a map of what we think isotopic signatures should look like over large scales. We do know that climate plays a huge role in these so-called terrestrial isoscapes. Also, if you're in a marine system, we have very different isotopic signatures than in terrestrial systems. But let's today just think about terrestrial systems. The map on the right, I'll show you one of these for Africa in a moment, that this is South America. And this is what, this is a theoretical map. This is saying, what do we think plant composition should look like isotopically for carbon across the continent of South America? Well, obviously people didn't go and measure these points all along the map. They modeled this based on climate, elevation, humidity, all those good things. So this is a theoretical map, but it's been ground truth to some extent. But the plant physiologists have come up with these maps, and this has been a great boon to us, and I'll explain that in a moment. But all you really have to know is that, wait a minute, what if a bird grew its feather in the Amazon here and then flew down to, southern Brazil or northern Argentina? Could we take its feather and then assume that we could pin it back to some of these places because it has very different and distinct isotope signatures? So that's the game we're going to play. And I have given Elizabeth a PDF of my talk. So there's a PDF version out there that you can use. So don't worry about if you miss some of this. But these are a list of the kinds of isoscapes or systems that people have put together through time. There's a big difference in isotopes between terrestrial and marine food webs. Even within marine food webs, there's a big difference between inshore and offshore food webs. Again, I won't explain why, but there is. And then in terrestrial systems, there's these big differences between photosynthetic pathways of plants. C3 plants, mostly in temperate areas. More in tropical areas, you get a lot of C4 plants. And then CAM plants like cacti and so on have very different isotope signatures. Also in dry conditions versus moisture conditions, we get big changes. And then more to today's talk, latitudinal and altitudinal gradients can lead to these big differences in hydrogen. Sometimes you'll see it as D, deuterium, and carbon isotopes. And I'll be showing you some of these maps we've relied heavily on. And then the geologists have gone out there and they can tell us all about the heavier isotopes of some very heavy elements in the rocks that are out there. Okay, so there are these things called isoscapes out there, and just think of them as an isotopic map. All right. Now, if you're really interested in this, you ever wanted to pursue it, there are some nice books out there on isoscapes and how you can use them to track wildlife and so on. And so, again, there's some other good resources and so on. Now, the big breakthrough for us is with the so-called water isotopes. Now, what do we mean by that? These are isotopes of oxygen and hydrogen because water is only formed by those two elements. Now, the processes of evaporation and precipitation radically change these isotope ratios in the water, as you can imagine. In fact, it's the lighter water, the less heavy water that gets evaporated to form clouds, leaving behind heavier water. And then it's the heavier water that then precipitates out across continents. And then there's a temperature effect and so on. I won't go into these other than to tell you that these form very predictable and long-term lovely patterns across continents. And I'll show you some examples of that. Well, luckily for us, the International Atomic Energy Agency in Vienna have spent the last 60 plus years putting together precipitation isoscapes from all of these locations, even from ships out at sea. And what they've done is they've been doing this not to benefit people interested in bird migration. They've done this to benefit knowledge of where water's coming from, aquifers versus precipitation, and these kinds of patterns. And the way this was originally formed, by the way, was to track nuclear explosions at atmospheric bomb testing in the 1950s. Okay, so we've inherited a data set that was never made for us, but we have the stable isotope component of that data set that is saying, oh, you want to know what the pattern of precipitation, hydrogen and oxygen isotopes look like in North America? Well, we can tell you because we have a 60-year data set. And this is what it looks like across the world. And you will see where I am, which is right about here right now. There are these beautiful gradients and patterns that we see, and it changes across the world. Notably, they're very negative in these polar regions where it gets very cooler. So the heavier isotope is much rarer in those places, and they're much more enriched in hot, drier places, as you can see here. Now, back in the 90s, I chatted. This pattern was known for many years, but nobody had come up with the idea of whether these patterns were transferred up food webs to go to organisms that migrate. So back in the early 90s, I talked to Len Wassenaar here, who was a colleague of mine at the time. And he's an expert on this kind of stuff. And I asked him, well, do you think that the hydrogen in water that goes into foods and so on and what have you, could it end up in a bird, and could we use these patterns that we've known about? And he more or less says, well, let's try it. And so that's what we did. By the way, this is what the pattern looks like in North America. We get this beautiful gradient going from from south to north. Down here, it's very, very enriched values. And up here is very, very depleted values. But the point you need to know is that you get this lovely change as you go across the continent. All right. So what we did in those days is we got feathers from birds, from many, many birds of different species across the continent. And we simply asked the question, does the isotope value of your feather match what we would have predicted from the precipitation that we know about and we've known about for some tens of years that the IAEA have been putting together? And when we put together what it was well over 1,400 data points of many different species from many different studies, this is the relationship we came up with, which is the feather isotope, deuterium hydrogen isotope feather, versus the precipitation average you would expect for the food web at that place based on precipitation. We get this predictable relationship. Now, there's a lot of noise here, and we've been spending a lot of years trying to work out, why do we get all this noise? But for the moment, this was a very powerful relationship, and you could say, these birds are from hot areas in the south. This is all North America, and these birds are from the Arctic, and all you guys are from points in between. So we had a tool, and it was a big breakthrough. And so we could create then a feather isoscape for North America, and this is what it looks like. Now, here's the thing. In North America, birds that are migrants that go down to South America and Central America grow their feathers here, and then they take them down to their wintering grounds. You know that it's the opposite in Europe and the Afrotropical system in Europe, and I'll get to that in a moment. So what we have are birds growing their feathers in this beautifully well-described isoscape. Then they take the feathers with them, and then we could say, well, if we take your feather down here in South America where you've migrated to, we can predict roughly where you came from in North America. So that's what we've done. I mean, we've spent a lot of time doing that. The basis of this whole approach is to take an isoscape based on whatever element, figuring out what this change relationship is, and we do that in captivity, or we can do that by marching across the continent of known origin specimen. We can create a tissue isoscape, which is this one for a dragonfly wings, and then we can start placing individuals as to roughly where they come from, and then we can summarize that with all kinds of special probability statistics, which I won't go into, but it's a way of doing this kind of work. So we've marched down to the wintering grounds where we know where a lot of these birds winter, and we've gone to these various places, and we simply asked, where are you coming from? So we took a feather from these birds, and these are Tennessee warbler and mourning warbler, painted bunting, and wood thrush. Okay, and then we've back projected where we think they must be coming from, and we've delimited it by their breeding range. And we've said this Tennessee warbler population from Guatemala, this is from one site, all these birds are from one site in Guatemala. You must have been coming from this region of North America. However, the mourning one, yeah, you have had to be coming from this region. And the wood thrush way down south, down here, and the painting bunting again down south, and so on. So without marking any of these birds, just by simply taking a feather, we've been able to work backwards and come up with this. Now, we've been lucky because we've had a lovely isoscape to deal with. All right, what's the story in Europe? Well, here's what the gradient looks like in Europe. And by the way, this has been really well worked out because as you can imagine, Europeans are extremely fastidious about taking water samples and running them through mass spec labs. And so Germany has 1 million of these points, okay? Other parts of the world have almost none, but you know, there is some data there that is just beyond belief. It is unbelievably good. This is what it looks like. It kind of follows the same pattern in North America where you have going from hot, dry areas to cool north areas. We get this gradient, but there's a lot of ambiguity, as you can see in Central Europe. That's okay. This is what it is. We're stuck with it. It's only one isotope, remember. So you're only using one variable to tell you where something is on a two-dimensional landscape. So there's going to be some variability. So we got Peter Prochaska from Czechoslovakia to go running around and take reed warbler feathers from known breeding sites. And he did the same thing we did in North America. He plotted their feather values versus their precipitation values for those sites. And look at this. This is brilliant. This is a beautiful relationship. So these feathers are really telling you where they're from. This, by the way, and Elizabeth is sitting in Constance right now. These points are from Lake Constance. These outliers. What's going on here? Well, if you know a little bit about the Rhine River and Lake Constance and you know, snow melt and where that water is coming from, it's actually coming from, it's coming from a different isotopic regime. And so this was not a good sample, but everything else is run by precip at that location. So in Europe, we also have a very good situation of telling where things are from. The problem is, most of our migrants don't grow their feathers in Europe. They grow their feathers in Africa. And so what we really would love to have is a really good isoscape for Africa so that we could say, your feather was grown in this part of Africa. Okay. Well, I'm just going to give you a few little examples of what we've done in Europe, despite some of the ambiguity. These are woodcock that have been shot in Spain. Every year, woodcock migrate down to Spain where they are hunted. And we asked the question, well, where did you come from? It looks like most of them are produced in Central Europe and then are harvested, killed in Spain. Okay, so you can do this with hunted birds because you have lots of material. And the wood pigeon is a bird that is also a migrant, and it's a very popular hunted species. And every year we get them wintering in Corsica, off of Italy, and vast numbers of hunters go over there to kill them. And we ask the question, where are you coming from? Because we can get feathers from them. It looks like they've been produced mostly in Eastern Europe, and this has been delimited by band return information. But they're coming not from this part of Europe, they're coming from the eastern part of Europe and so on. Okay. And we've looked in the Italian Alps with another study based on pied flycatcher and robins, going through the Alps. And this is where the isotopes would tell you they're coming from. But then we've said, let's get clever here, because there's been so many birds in Europe that have been banded or ringed, millions, that we also know what the trajectories of travel are of these birds, as well as the isotope data. So what we're going to do is we're going to put the isotope data together with the ring recovery data, and we're going to tell you, oh, we can do a better job than this. And this is where we think they're coming from, based also on what we call prior knowledge of the band returns. And so you see it's getting down into some pretty narrow parts of geography here. So combining isotopes with other information is an area that is of great interest. Using genetic markers as well as band returns can really refine some of this work, and that's what we've been doing. Okay, but I know most of you have been interested in applications and are interested in applications in Africa. And what I will say to you is, hey, it's complicated. Okay, Africa is very complicated climatically and with the amounts of rainfall, as you all know. And so while there's been a lot of really wonderful isotope studies in Africa looking at archaeological remains and all kinds of things, it's a very challenging continent to work on. The other thing is that the IAEA in Vienna have data from Africa, and it's getting better, but they don't have a lot of precipitation data compared to, say, Germany. So we're at the mercy of an isoscape that is not as good as we'd like it to be. So if you hear people saying to you, oh, you can't use isotopes in Africa, they're actually wrong. But secondly, part of this resolution issue comes down to our need to improve the isoscape, which is what we're in the process of doing. It's a long history of applications of isotope tracing in Africa. This paper included 2 papers in the same issue from South Africa, but it was based on trying to trace African elephant ivory from the illegal trade, obviously, but they were able to fingerprint using nitrogen isotopes and strontium isotopes from these national parks. And they could say, well, you know, your ivory did or did not come from this national park based on the isotope data. So here's a fingerprinting way of doing this, and it's actually quite impressive. They were able to really narrow down sources of African ivory. And this is a process which has been ongoing for some time now. So they've refined this. This has gone back, 30 years, but it's ongoing. This forensic tool is ongoing, and they're using other isotopes, not just hydrogen that I've been talking about. But what I decided to do for Africa is to tap on the shoulder of plant physiologists, people who've spent their careers trying to map, using these models, these climate models, of what they think the plant composition should be like photosynthetically across whole continents. So Chris Still and Becky Powell have been doing this. Their whole career is based on coming up with these kinds of depictions, seeing how they change through time, how plants respond isotopically in terms of their photosynthetic evolution to climate. So he said, oh, well, if we consider a few things about C4 and C3 plants in Africa, this is what we would predict the composition, this is the average composition of plants in Africa to look like isotopically. And I thought, well, it's not ideal because we know birds don't sample the entire food web indiscriminately, but it's a starting point. So what I did, I took this map and I said, well, what would a feather look like if it was grown in each of these pixels? And we knew what those isotopic relationships were for these various elements. And so this is what a feather isotope isoscape should look like for Africa. Okay. And so, we would predict that, these values be very low, very moist area in the Congo. And, we would expect in general the food web to be much more depleted in carbon isotopes than in these drier areas and so on and so forth. And elevation comes into this, a number of things. Okay, so we have one surface for carbon isotopes of feathers. Then a guy by the name of Chris Crane, who spent his career looking at nitrogen isotopes in the world, and he has again come up with models for climate and how that should affect nitrogen isotope values under natural conditions in plant communities. And he came up with a world, prediction of what nitrogen values should be in plant leaves. Okay, this is what people do, all right? And I said, all right, well, let's take your map for Africa, and we'll come up with a feather nitrogen isoscape for Africa, and it should look something like this. Okay, now nitrogen is very problematic because if you have agriculture and you put fertilizers on fields and you do all kinds of things, all rules are out the window. But this is just a starting point. So this is what we did. And then, of course, we have hydrogen, which is based on the long-term 60-year average of the IAEA in Vienna. And so we have 3 isoscapes that we can put together. We can take a feather and run it for 3 isotopes. And we could ask, do we get a better idea where you're coming from? So we can do all kinds of little games with that. And what I did initially was to just say, all right, I'm not going to look at a continuous surface here. That's hard to do with 3 isotopes. I'm just going to show you areas which have the same value, the cluster of the same isotope values. So isotopically, this is what Africa looks like using carbon, nitrogen, and hydrogen isotopes all put together into a package. And you ask, how do they separate spatially? And we're going to call those 4 clusters, 1, 2, 3, and 4. And we're going to say, okay, well, we don't, there's a lot of ambiguity here because you've got a red area here and you have a red area down here. So that's not very good for us. But this is what it looks like. So we asked the question, well, what could you do with this information? Well, a colleague of mine, Cosme Lopez Calderon in Spain, has been working for a long time on house martins. And house martins were growing in Seville in Spain. And then they migrate down to West Africa here. And from all the geolocator and band returns, we know this is pretty much where they winter. They winter across this kind of area. So that was already known. So that was good. And so if you blow up this area to those clusters that I talked about, cluster 1 is actually savanna, cluster 2 is actually savanna, is this orange color. It's open country savanna, whereas cluster 1 is more broadleaf moist forest. Okay, so you have this big biome change across here. And this is kind of what it looks like, okay, with these 3 clusters. Then in Spain, he took the feathers of these birds, and they have long-term study. They've been taking feathers from these birds forever. And he asked some questions about, what do we know about where you wintered? And what can we say about its effects on you when you come back to the breeding grounds? And this is what he found. He said that if you wintered in cluster 2, which is based on just running them through the mass spec, and that's where they came from, and experienced and young birds, doesn't matter. If you came from cluster 2, you got back to Spain earlier. You initiated your clutches earlier. You actually did better than the birds that wintered in cluster 1, which is the moisture area. They had to stay there longer. They came back later. So if you get back early, you tend to do better on the breeding grounds than if you come back late. And that's what he found here. And then he also found that there's a sex effect, but also an age effect. And look at this, with males, those that were assigned to cluster 2, which is the drier savanna areas, the experienced males did were coming mostly from cluster 2, whereas the inexperienced males were not. So there's some kind of segregation going on those breeding grounds. Now, I haven't told you what piece of real estate these birds have come from specifically, but I have told you about the biome that they're coming from. And we've used this information. We've used it. This is a technique we've used on redstarts in North America and so on. And so we've been inferring back what kind of habitat you were in. And it's interesting that these house martins in Europe, breeding in Europe, but wintering in West Africa, they do better. They seem to do better in these open savannas than they do in any kind of forested biome. Other birds, of course, are dramatically different, but that's what they found. Cosme went on to look at barn swallows, and I won't go into this. It's basically, again, what I've already told you. You take 3 isotopes, you come up with and this time, instead of those 3 clusters, he's cleverly put this together statistically into a Bayesian model where he's looking at a continuous isoscape. All right, I won't go into that other than now we can look at probability of origins. And he can delimit that by all the band returns of the species from Europe. And he can say, well, we're going to put a much higher probability on this band, and so on. So we're putting that prior knowledge together with the isotope data. And he says, if you do that, we think these birds are coming from here. Now, let me quickly say that if you look at geolocator data from Europe, we're starting to see some differences between the isotope data and the real geolocator data. And what we think is happening here is we think these birds winter in really marshy riparian areas in Africa, and that is very hard to model isotopically, because you can have a C4 biome and C3 plants just along these little riparian edges. So some species are not going to work well for us, but others will. So you have to be a bit careful. And again, I could go into that. But these are the kinds of path analysis diagrams you can come up with. This is not based on exact geography. This is based on just the kind of place you were in. And we can associate that with the natural difference vegetation index. That is an index of green up or productivity on the wintering grounds. And we can say, moisture, whatever, it's going to have a real effect on your breeding date when you get back to Europe. And people play these games with these path analyses. The net result is you can relate fitness to where these birds wintered, and that's where the isotopes come in to help us out. Okay, that's a long way down that pathway. We've worked on a similar kind of thing with the, this is a wood warbler. This is from the Bielowice forest in Poland. And they've been banded for years, but they never get a return. They band thousands of these things, and they never get a single bird back with a band on its leg. So they can't really tell anything about these. So what we did was run their feathers, and we have a hydrogen, carbon, and nitrogen isoscape, and we put all 3 together, and we think they're wintering in this area. Now, nobody can prove us wrong, and I've just told you a story. So one of these days, it's a hypothesis. We're hypothesizing that this area is where you should go to look first, or if you're going to put geolocators on these birds, although you'd never get them back because they wouldn't come back to your breeding site, at least in the Bielowice forest. This is the game we've played. Okay, so I'm guilty of telling stories, but it's a prediction, and I think it's useful. Well, since that's been all happening, most recently, I've been working with people in Israel of the migration through Israel, Eilat, and places like that, and the Jerusalem banding station and so on. And they've looked over time with feather isotope values of these birds, and knowing what their distribution is in Africa and based on citizen science and distribution models, we've combined the isotopes with that to come up with where we think their populations of birds are wintering and growing their feathers. So I think this has reached, if you like, the limit of sophistication of what we can do with isotopes and putting it together with other bits of information. But I think there's a great future in continuing to do this kind of work. And I think Elizabeth is particularly interested in doing this work for at least for East Africa as well. And I think there's just a great future in doing this because, to be honest with you, it's relatively easy. The other thing is our isoscapes for Africa are going to become more and more refined as we get more and more precipitation data. Nothing special about birds. The painted lady butterfly has been studied incredibly in Europe. It's a migratory butterfly, and they breed in Europe and they migrate down, and they have been sampled in this part of North Africa and so on. And in the spring, they capture these butterflies with very new wings. So they haven't been very worn, they're very new wings. And they infer that they must be young of the year, or they've been produced most recently. They haven't been traveling a huge distance. So you have old animals that are really worn feather wings, and those. So they know that these things get down as far as the sub-Saharan region and the Sahel. And so what they've done, and the isotopes have informed us with this work, is that yes, the ones that are coming back this far in the spring before they head up into Europe again were actually produced in the Sahel region of Africa. So here's a way of running the wings of these butterflies and putting that story together, much as we have with the monarch butterfly in Europe. Now, I'm just going to end by telling you the story that Elizabeth enjoys, which is dragonflies. Now, we've done the same thing with dragonflies in North America. We've taken them from all over the continent, from their natal wetland from which they're produced. And we've asked the question, how does your wing isotope value correlate with the mean annual precip value? And we get these lovely relationships again. So we can put together a dragonfly wing isoscape. Now, it's the only one that exists in the world. We're the only people that's tried to work out this relationship. So we're assuming that all dragonflies in the world will follow this relationship, which I think is reasonable, because all you're doing is taking water, hydrogen, making a wing out of it. And that shouldn't change if you're in India or if you're in North America. Well, we've got a nice dragonfly relationship to work with. So then I was watching, I don't know if you guys know what a TED talk is. It's on the internet. It basically, they get these really interesting people to give a 40-minute talk every now and again. And I was tuning into it, and there's a guy by the name of Charles Anderson, who's a great guy who's a marine biologist, but he lives on the Maldives island off of southwestern India. And every October, he notices there's a big fallout of dragonflies, of Pantala flavescens, which is the globe skimmer dragonfly. There are no dragonflies produced on the Maldives. There's no standing water on the Maldives. They have to be coming from somewhere else. So every October, they drop out of the sky and everybody runs around and the kids pick up the dragonflies and there they are. So the big question was, where do they come from? And he gave this talk saying, well, I think they're coming from well into India. And I think these dragonflies are heading over to Africa. Well, if you look at the winds at the surface of the Maldives, they're actually in your face. So it would be hard to imagine that a dragonfly could fly against the wind to get to Africa from the Maldives. But if you go up 1,000 meters or 2,000 meters, the winds are in the opposite direction. The winds aloft are actually in the other direction. So he speculated that these dragonflies are coming from India somewhere. They're crossing the Maldives at high altitude. Some of them drop out over the Maldives, but where they really want to go is East Africa. Okay. And then he said they're going to breed in East Africa. They're going to, several generations later, they're going to make use of these winds, these southwest monsoonal winds, to take them back so that you will have a migratory loop that is eventually fulfilled, and that several generations later, they will return to their origins, and that you would have this kind of spatial movement pattern. If true, it would be the longest insect migration ever recorded, because this would be multi-generational, but it would be 14,000 kilometers. So it's a very exciting story. So I contacted him and say, look, can you get a hold of some of these in the Maldives and send them to us, and we'll try to work this out. So we looked at all the available precip data for India, and we found that there's a very distinct pattern in India of precipitation and standing water, both standing water and precip. We looked at it both ways. So the isotope data say these values in northeastern India are very negative, and they're very depleted. But as you go south in India, they get very, very positive. We ran the dragonfly wings, and lo and behold, there's no way they could have come from southern India. They had to be coming from at least this far, the Himalaya region, or right in the northern areas of northern India, and possibly beyond. And I think they may well be coming from the Mongolian plateau, the Tibetan plateau, well up here where they have much nicer habitat. Anyway, that's to be looked at. So we said, oh, we think that's what's happening. Well, since that time, we've had some dragonflies sent to us from East Africa that we're looking at. And sure enough, they seem to be matching the same story, that they seem to be coming from this migratory route. And recently, some Russian scientists have been collecting the same species in Kazakhstan, and they have put together what they think is the same story, that, you know, that last generation that comes back up and are breeding up in this region, that's what we seem to be seeing. So very hard to prove, because how do you put a transmitter on a dragonfly? But in short, then, what we think is happening with the globe skimmer, which, by the way, is just an amazing animal that is dispersed throughout the world. You can have a population of this in the middle of the Pacific Ocean. We've been doing work on them, presumably breeding in China and ending up in Japan. That was been our latest look. But there's a neat story still to be told, where we think that this is where they're originating, a big part of them coming through the Maldives, getting over to East Africa, where they lay eggs in wetlands. That next generation keeps moving north, and eventually, when those monsoonal winds kick in, they can make use of those and get them back into a migratory loop like that. So that's what we think is happening with the dragonflies in Africa. Most recently, we've looked at feather sulfur isotopes in India from museum specimen. And all I want to show you here is that the sulfur isotope values in this part of India, because of the geological history, are very, very low, the very little of the heavier isotope of sulfur compared to the rest of India. So I'm really keen on getting enough of these dragonflies run for sulfur now to see if they also mimic the same pattern that we're seeing, and so on. So it's all a work in progress. Well, final thoughts are, I've just told you about bulk tissues. I've only talked about a couple of isotopes. The periodic table is filled with isotopes. There's a lot of stories and a lot of useful tools out there that could be looked at eventually. People these days are less interested in looking at bulk isotopes. They're taking those feathers and they're breaking them down into their essential amino acids. And they're looking at the isotope values of those amino acids. And they're getting very sophisticated and very clever at this kind of work. I would say it's not absolutely necessary at all, but this is where the field is seemingly going, looking at more elements and looking at more compounds and so on. So I will summarize by saying, for applications in Africa, isoscapes need much more refinement, no question. But luckily this is happening. The IAEA are sending laser machines out all over Africa so that precip can be run without sending those samples back to Europe, etc. It's getting better. But remember that applications can also indicate the type of habitat better than geographic locations. And that can be exactly what you're looking for. You may be asking the question, does your bird grow its feathers in mesic, wet, cool environments, or in hot, dry environments? And how is that changing through time? Does that affect when they come back and migrate? Does it affect when they arrive back in Europe all of those kinds of questions. And I will say that isotopes never lie, okay? They actually are what they are. They're telling you what the isotope value is, and it's up to us to interpret it, okay? So we can formulate hypotheses based on these, but it's not that the measurement's wrong. It's that maybe our theory might be wrong, and we may have to modify them as well. Okay, I will leave it at that, and I will just remind you that if you have any, burning questions or whatever, you can always email me, and Elizabeth will have that information. But I've also put this on a PDF, and I think if you ask Elizabeth or myself, we can send you that PDF file as well. So thank you for your time, and I'll leave it at that. Thank you very much.